This just some highlights of these spectral functions. When we're talking about a spectrum, right, the output of a Fourier transform, we get magnitude and phase, or we can say real and imaginary, and we just want you to, hopefully we highlighted the need to be careful when averaging. An auto power spectrum, we're just talking about the magnitude of the spectrum. This is probably more widely used than spectrum, I think, a lot of times too. People are just interested in the amplitude and maybe your frequency content, and just because you don't have the issues related to averaging necessarily. A little safer to use if you're unsure. Now we're going to move on to power spectral density function, or PSD. And it's just building again on a previous function, right? We built on spectrum to get the auto power. Now we're going to build on this idea of an auto power to get a PSD. And we're just talking about the magnitude of the spectrum, an auto spectrum, normalized by the frequency resolution. So you'll have units of like G squared per hertz, and probably a really big application, you're probably using this right now, is like shaker table testing. A lot of people use PSDs there, and you can kind of see the DSP format of how it's written. Basically, we're talking about that auto power divided by the frequency resolution that we have set. And we're going to look at a demo now by Pete on how spectral lines on auto powers with random data.
All right, and maybe to point out here what I'm doing, I got a SCADAS data acquisition system. I am going to use a highlighter here. And what I've done with my SCADAS is it has a built-in signal generator. So I'm taking the output of that signal generator and I am looping it over to the first input on my SCADAS. So I'm just measuring the voltage coming out, a high precision source. So on that signal generator, I've set up a random signal, 2-volt level. So here I have my screen again, and it's the same setup as before. I got a random signal that I can play out. And this time, I'm just going to measure an auto power by itself. Oops. On test setup here, we got auto power. I have a 1 hertz resolution, 30 averages. I'll go here, hit measure, and this will take a little bit of time in order to measure 30 averages. So it's going. If I'm looking at phase, it looks pretty boring, but if I look at amplitude, I'll see the signal. We can see that anti-aliasing filter that you were talking about, Charles.
Mm-hmm.
And so this one is, I guess, going to be run 2 when we're done here. So I got a 1 hertz resolution, almost finished. And we're doing this in real time, so you know we're not cheating. Now I'm going to take the same signal, go to 2 hertz, and measure it. This might take a little less time, like half the time, because it's 2 hertz resolution, half-second acquisition. 1 hertz resolution was a 1-second acquisition. So we're getting
smaller
30 averages.
Yeah,
a little less time. And then I'll go here and I'll say, same signal I'm going to measure, but now I want to do it with 4 hertz. So it's this random signal, and I'll hit start. Oh yeah, that's smoking fast. And when I'm done here, I'm going to go into the navigator and I'm going to overlay those 3 measurements that I just took. So I'll open a display. I believe that was 1 hertz. Now, this is the 2 hertz. Do we expect that to be different, Charles?
I expect that to be different.
It's the same random signal.
I know. We'll talk about that in a second, though.
Looks a little bit different, yeah. And then I had so that was 1 hertz, 2 hertz, 4 hertz. Same signal, same 2-volt level, if you will, yet 3 very different looking spectrums. And I think you're going to talk to why they might look so different there, huh, Charles?
Yes. So we're going to kind of use a short example here to kind of illustrate why those auto power spectrums look so different when it's the same signal. So imagine a pitcher with your favorite beverage. No, I'm joking. Also, let's think about this as being random broadband spectral content, right? So this picture is filled up to the same amount. And we're going to have 3 glasses here, right? So we have a bandwidth of 6 hertz, and our delta F is 2 hertz. So we have 3 glasses then. And we're going to pour our spectral content, our beverage, into these 3 glasses, right? And it's evenly poured. It's a broadband, random spectrum signal. Now, take that same picture, fill it up to the exact same amount of spectral content. And on this side, though, we have a bandwidth again of 6 hertz, but now our delta F is 1 hertz, right? So we're going to have actually 6 glasses, right? One glass at each spectral line there. And if we fill that up, same amount, we can see that there is a difference in level. There's an amplitude.
Right, the random gets spread evenly amongst either the 3 or the 6 glasses, huh?
Yeah.
That's what that random does, yeah.
Yeah. So when we talk about a PSD, we said, right, it's the auto power normalized by the frequency resolution. So what if we normalize by the frequency resolution here? What happens? Well, if we divide by this 2 hertz, then our level drops to the same as here, right? So if we're using a PSD, and over here we would be dividing by 1. So that's what the PSD allows us to do, is to normalize that auto power signal such that even when we're using different frequency resolutions, we won't have that appearance of it being a different level. I think, Pete, you're going to show that in the software even, right?
So here, little feature tip, I can say duplicate. So I have my original plot, my new plot. So these auto powers, if we were to zoom in a bit, you can see that blue has fewer data points, but they're higher amplitude. Green has more data points, lower amplitude. Red has even more data points, lower amplitude. If we were to take all these, an important thing to realize when you're using the software, let me switch that to curves, line segments, is if I was to do something like a double X cursor, which would sum up all the energy here in this signal. So blue has fewer data points, but summed together, I say calculate RMS. Notice that for all 3 of these curves, even though visually they look very different, they all have the same exact energy, 0.52, roughly. So don't be misled by the way it's being represented there. If you go back to this RMS, you get the right stuff. I have all 3 selected, and up here there is a thing called a format conversion, and I can say, well, I want to convert this to a power spectral density, which will divide the 1 hertz by 1 amplitude, the 2 hertz by 2, the 4 hertz by 4, etc. I hit OK, and lo and behold, all of them are the same. Notice the RMS didn't change. It's identical still, same it was for the auto powers. It's the same information. But now visually, they all look alike using the PSD. All right, so back to you, Charles.
Thanks, Pete. So we've been talking about random signals, right? So with the auto power, the levels are going to be different. With PSD, the levels will be the same. But what happens if we're talking about sinusoidal signal? Pete, you want to show us what could happen if we're talking about a different type of signal?
Yeah, I switched it from random to sine. Hopefully you saw that. And I switched it to 2 volts here, so we can see a nice sine wave. And that sine wave is at 100 hertz. And so I'm kind of just going to do the same experiment with the sine wave. When I go to measure, I'll start out since we're already on 4 hertz. We know that it was 2 volts. I'll hit start here. Looks like I have a nice 2 volt sine wave over 30 averages, which is great. And then I'll go here to 2 hertz now, and we'll do the same measurement again. And notice it's still 2 volts, which is, I guess, what we would hope for. Although trying to remember, with a PSD or with a auto power, which is what I'm using, when we changed the frequency resolution, the amplitudes started changing. Here, let's see if this is still the case, as I change my frequency resolution, the amplitudes are not changing. So that's different behavior between the random and the sine. And we'll take a look at these in a second and compare them and see if indeed what we were seeing here on the screen during the measurement is actually the case. So, go to the navigator here, open a new display. The last 3 measurements I just took, I got 3 spectrums, and you can see they are all identical. I'll move that out of the way here. So they're all 2 volts. Now, Charles, he's going to explain why that's all 2 volts still. Looks like I didn't copy them all in there for some reason. I don't know which one I missed. Maybe that one. So if I was to take these and I switch them under the format conversion now to PSD, all 3 are different: red, green, blue. And if I go back to auto power, they're all the same. So maybe you can shed some light on that, Charles.
I will try. When we're using a sinusoidal, and I should say periodic sinusoidal signal, meaning that we're lining up with the spectral line, or we're putting all of our spectral content here. Turn my pointer on. All of our spectral content here into one glass and the one spectral line. When that's the case, if we were to normalize by the frequency resolution, in this case with the PSD, we would be decreasing the amplitude, right? That's why with a PSD, it's generally not a great idea to use a sinusoidal signal. If you're going to have a PSD, sinusoids is not a great idea because the levels are going to be different. So if I divide by 1 hertz or 2 hertz or 4 hertz, it's going to change this level, right? Whereas when we're talking about an auto power, the levels are all going to be the same, because no matter what frequency resolution or spectral lines I have, it's all on one glass. It's all on one spectral line. Does that make sense for you, Pete?
Yeah, so if I go to a party and you're the host, Charles, I want you to treat things like a sine wave. So you put all the beer in my glass. Whereas I don't want you to act like a random signal and distribute the beer around.
Okay.
Am I getting the right conclusion here?
You're getting the right conclusion. So
the other party goers may not be too happy, but I would be happy because I get everything by being sinusoidal.
Well, summing this up again here, when we're talking about random signals, if we're using an auto power, the levels are going to be different when we change the number of spectral lines, but with the PSD, the levels will be the same. And it's the reverse if we're talking about a sinusoidal periodic signal. With an auto power, the levels will be the same, but with the PSD, the levels would then be different.